Welcome to Study Loop.
So in this problem, we are given with the decomposition reaction of sulfuryl chloride, which decomposes to give us sulfur dioxide and chlorine gas. We're given the number of mole of the reactant sulfuryl chloride, which is 2 mole. We are given the volume of the reaction vessel, which is 2 liter. We're given the temperature at which the reaction is taking place, which is 303 Kelvin. And we have said that if 56% of the reactant sulfuryl chloride decomposes, what is the value of Kc, what is the value of Kp. So these are the first two questions of this problem. So first we'll find out the value of Kc, and to find out the value of Kc we have to know the equilibrium concentration of all the components here, the reactant and both the products. And to know their equilibrium concentration, what we have to do, we are given the number of moles and the volume of the reaction vessel. From where we can find out the initial concentration of the reactant sulfuryl chloride. And then, as we have said that 56% of this reactant decomposes, that means from this value we can find out the change in concentration, and from that we can find out the equilibrium concentration for the reactant and also both the products. And from all the equilibrium concentrations, you can find out the value of Kc. So what we have to do is first you have to find out the initial concentration of SO2 CO2, which will be simply its number of moles over volume. So the initial concentration of SO2 CO2 will be the number of moles, which is 2 mole, over the volume, which is 2 liter, and will give us 1 mole per liter, or 1 molar. So this is the initial concentration of SO2 CO2, and 56% of 1 molar will be 0.56 molar. So this is the change in the concentration of the reactant. Now from these two values we can set up an ice table for this reaction. So the ice table will contain all the reactant and products. The reactant here is SO2 CO2, which is a gas, and it will decompose to give us SO2, a gas, and Cl2, which is also a gas. And the initial concentration of SO2 CO2 is given as 1 molar, and then since at the beginning we don't have any product, the initial concentration of both the products will be 0. Then the change in concentration is, I will just calculate as 0.56 molar. The change for SO2 CO2 will be minus 0.56, and for SO2 and for Cl2 it will be plus 0.56, since the coefficients for all the reactant and products are 1 here. So if we look at the balanced equation, here we can see that 1 mole of SO2 CO2 decomposes to give us 1 mole of SO2 and 1 mole of Cl2. That means um, the change in the concentration for the reactant will be equal to the change in the concentration of the products. Just the sign will be the opposite, because in case of reactant the concentration is decreasing, and in case of products the concentrations are increasing. And then the equilibrium concentration will be for SO2 CO2 to be 1 minus 0.56, that means it will be 0.44, and for these two it will be 0 plus 0.56, that means 0.56, and for Cl2 it will be 0.56. So now we know equilibrium concentration of all the reactant and products, and from these values we can find out the value of Kc, as we know that the value of Kc is equal to product concentration over reactant concentration. So both our product concentration are 0.56. We can write 0.56 times 0.56 over the reactant concentration, which is 0.44. So all of these are the equilibrium concentration, as we know that Kc is equal to the equilibrium product concentrations over the equilibrium reactant concentration. And from here we'll get a value of 0.712, and this is the value of the Kc for the reaction given at the given conditions and at a temperature of 303 Kelvin. Now in the second part of this problem, we have to find out the value of Kp from the value of Kc, and we know that Kp is equal to Kc RT over del N. Here Kc is just calculated. R is the universal gas constant. T is given as 303 Kelvin, at which we have calculated the value of Kc, and del N is the difference between the number of moles of the products and reactants. So the if we just plug in the values, the value of Kc we have calculated 0.712, universal gas constant value is 0.08206, the value of temperature is 303 Kelvin, the value of del N, if we just look at this, we can see, as I've said, it is number of molecules of reactant minus number of molecules of product. So we have 1 plus 1, total 2 molecule in the product side minus 1 molecule in the reactant side. We are asked to find out if we so if the reaction mixture is transferred to a reaction vessel of 15 liter, would the percent of H2CO2 that decomposes will increase, decrease, or stay the same? So if we look at the balanced reaction equation here, we can see that one molecule of SO2 is given as two molecular products, and from the Le Chatelier principle, we know that if we increase volume, then the reaction or equilibrium will move in a way where there are more number of molecules present. So I repeat one more time, according to the Le Chatelier principle, if we increase the volume, that means we are decreasing the pressure, and in case of decreasing pressure or increasing volume, the equilibrium will shift in a way where there are more number of molecules present. So if we look at this reaction balanced equation, we can see that in the product side we have more number of molecules, since we have two molecules in the product side and one molecule in the reactant side. That means if we increase the volume, since we are increasing the volume from 2 liter to 15 liter, that means we are increasing the volume, and according to Le Chatelier principle, the reaction will go forward. That means more SO2CO2 or sulfuryl chloride will decompose if we increase the volume to 15 liter. That means the answer to this part C will be the decomposition will increase. Now in part D of this problem, we have to find out the percentage of decomposition in 15 liter vessel at 303 Kelvin temperature. So at 303 Kelvin temperature, we have already calculated the value of Kc, and we know that at a certain temperature, the value of Kc remains fixed for a reaction. That means even though you're changing the volume, the value of Kc will be unchanged, and the value of Kc we have calculated as 0.712. If you write the expression one more time, the expression for Kc will be the product concentrations. So products are SO2 and Cl2, so it will be the concentration of SO2 times the concentration of Cl2 over the concentration of reactant, which is SO2Cl2. Now we know the value of Kc, which is 0.712. Now if we consider that the decomposition is so to find out the decomposition percentage, what we have to do is first we have to find out the change in the concentration of the reactant, and if we assume that the change in the concentration of the reactant is X, then we can set up an ice table for this, which will be from here we can find out the equilibrium concentration for each. So for the ice table, we will have SO2Cl2, and the products will be again SO2 plus Cl2. Now, what is our initial concentration of SO2 Cl2? The initial concentration will be, now our number of moles is still the same, which is 2 mole, but we have increased our volume from 2 liter to 15 liter. So it will be 2 mole over 15 liter, and this will give us a value of 0.133 molar. So this is the initial concentration of SO2 Cl2. It will be 0.133, and the initial concentration of both the products will be 0. And if we assume the change as x, so for SO2 Cl2 it will be minus x, and for both the products it will be plus x. And the equilibrium concentration will be, for the reactant it will be 0.133 minus x, and for both the products it will be x and x. So these are our equilibrium concentration for reactant and products. And now if we just plug in these values here, so we have already calculated the Kc value as 0.712, and both the product concentration are x, so we can write x square on the numerator, and as the denominator we will have to write the change the equilibrium concentration of the reactant, which is 0.133 minus x. Now if we rearrange this, we will have a quadratic equation like x square minus x square plus 0.712 x plus, now it's minus 0.095 equal to 0. So this is the quadratic equation, and if we solve this equation for x, since we know that the solution for quadratic equation is minus b plus minus root over b square minus 4ac over twice a. So if we solve this equation using this formula, we will have two values for x, and those are 0.115 or minus 0.827. So since x is a concentration and it cannot have a negative value, that means we cannot accept this value, so the value of x is 0.115. And from the ice table you can see that this is actually the change in the concentration of the reactant. So the change in the concentration is 0.115 molar. So the percent of decomposition will be change over original times 100, and it will give us the percent of decomposition. So the percent of sulfuryl chloride decomposes in this case will be 0.115 over 0.133. So the change over um, initial times 100%, and this will give us a value of 86.47%. So this is the decomposition percentage of sulfuryl chloride if we transfer the reaction mixture to a reaction vessel of 15 liter.